Hello, everyone. My name is Peter Robinson, and today I have got Francesco from Ethereum Foundation, who is going to tell us all about peer DAS, so data availability, actually, DAS. Anyway, look, I'll throw it over to Francesco, who's going to not only introduce himself, but remind me what DAS stands for, and go from there.
Hi everyone, thanks for having me first of all. I'm Francesco, I'm a EF researcher. I've been at EF for a few years now and kind of jumped around different topics. And yeah, for the last maybe a year and a half, 2 years, I've been involved with this blob scaling effort and DAS, which is data availability sampling. And yeah, I've especially been quite involved in the peer DAS effort for the last year. So yeah, basically my plan would be to kind of tell you where things are in DAS land in Ethereum today, and yeah, kind of where we're going with the next fork, and really kind of try to dig into some of the details of what's going on.
Brilliant. That sounds awesome. And yeah, please present your slides.
All right. Can you see well?
Yes, they are very clear. All good.
Nice. Okay, so yeah, as I said, Ethereum DS in 2025. Let's get into it. So, okay, yeah, everything works. Yeah, so first, before getting actually to DS, let's a bit recall like where we're coming from, like what's happening now with blobs. And yeah, that is EIP 4844, which came in the last fork. Essentially, as of last fork, we have these blob sidecars that go outside of blocks. They're essentially sent separately, and that just contain data that rollups post. So this like red blob might be like an optimism blob. This might be like an arbitrum blob, and so on. Yeah, I mean, I'm not going to go into the details, of the rollup-centric roadmap. I'm kind of assuming people know what the blobs are for. But yeah, basically, given the fact that rollups do want to post data to Ethereum right now, the way to do it is through these blobs. The kind of main two things that actually EIP 4844 did for scaling is one, that blobs now have this independent fee market that's separate from the L1 fee market of gas essentially. And then that blobs are only stored and served for about 18 days. So you don't store them forever. And is just two simple consequences, like because of the independent fee market, they're not competing with L1. So L1 could be quite expensive, but blobs can still stay relatively cheap. And also that there's no storage growth, like there's kind of a fixed storage associated to blobs. So it's much more okay to scale them up in that narrow sense. And this is a bit overwhelming, but like we'll see this a lot. So I think eventually you'll get used to the picture. This is kind of one way to visualize what the whole architecture of 4844 looks like. So there's the execution layer on the side, on the left side, and the consensus layer on the right side. We have these like get nodes, but like could be different clients. I just didn't want to bother copying a bunch of different ones for different clients. We have the blob mempool on the EL, and essentially, this might be like a rollup node or like a node run by a rollup that's submitting a transaction to the mempool, a blob transaction to the mempool. These blob transactions go around, they propagate, eventually they get to the proposer. In this case, the EL node of the proposer, the execution layer node of the proposer. Through the engine API, we kind of cross this barrier between the execution layer and the consensus layer. So the proposer runs like an execution node, a consensus node. The blobs get sent together with the block to the CL node. There's this lighthouse, but again, could be Prism, could be anything. And now we kind of are in the consensus layer side of things. The proposer needs to basically push out these blobs to the network as fast as possible. And the way it specifically does so is kind of similar to how it works with a block. There is a certain gossip topic, we call them, like a way to organize nodes so that they can propagate information. And so there's one for the block, and there's actually different ones for the blobs, and a different one for each blob. So not a single gossip topic for all of the blobs, but each one for each blob. So yeah, this red blob is going to be sent to like different peers than the blue blob. And then eventually, things propagate. They're supposed to get to attesters, these other beacon nodes. Yeah, that's kind of the critical path of consensus. Like they attest and we sort of establish consensus on the block and the availability of the data in particular. And yeah, so let's zoom in on the right side, specifically on this consensus layer networking architecture that exists in 4844. So I mean, this is basically the picture you already saw, the proposer and all these subnets. So one more advantage that it's not as obvious from 4844 is that we kind of see from this more specific look at the networking architecture is that, as I said, blobs don't travel together. I mean, for one thing, they don't travel with the block. So it's not this block plus blobs bundle, which would be the naive kind of way of going about sending out the block. They travel separately and in parallel, like quote unquote in parallel, but yeah, on these different kind of subnets. And this actually has like quite a lot of advantages. Like one way to think about it is on the right would be this naive way of doing it, where you just send this full kind of bundle of blobs all together. You would send it to 8 peers. This is just how Gossip Sub works, the way we propagate things. You kind of have a mesh of 8 peers, and you just send stuff to them. And yeah, on the left side is how it actually works with these kind of parallel gossip topics for each blob. So you would send each blob to 8 peers. And the total amount of data that you send is the same. You're sending each blob to 8 peers in both cases, but in the left case, which is what actually happens, there's this kind of much wider funnel where you basically get a lot more people to contribute with their upload bandwidth earlier in the process. Like very early, you get all of these nodes to do a little bit of work for you, essentially, in helping you propagate things. And yeah, in practice, you can see that it works out better, or also in simulations, you can see that it works out much better. Yeah, so we have these advantages that we talked about, but there is one kind of glaring issue that's not really been resolved, which is that nodes are still downloading all of the data. Like we have these, I mean, we're calling them subnets, which kind of stands for subnetwork, but in practice, actually, everyone is in all of the subnets. They're just the same as this kind of beacon block topic. So all of the nodes actually participate in all of them, and so they all get all of the data, which is ultimately not the goal. And yeah, so the question is, how do we move beyond that? And as you might expect if you come to this talk, it's through data availability sampling. So quick recap, what basically where data availability sampling comes from is, or like what's the core idea is erasure coding. So we take essentially, let's look at like this blue part this is the original data, and we split up, now look at it not as one big chunk of data, but as like split up into like finer chunks, essentially. Then we do some erasure coding, which I'm not going to go into like exactly how it works, but I mean, it's not something super specific to Ethereum, and essentially increase its size by 50% by adding redundancy. And now any 50% of this new data can reconstruct the full data, in particular the original part. And what this does is basically makes the problem of checking availability of a blob which would be like checking 100% of availability, like making sure that all of the pieces are there. It becomes making sure that only 50% of it is actually there, which is a much simpler problem. And the reason it is a much simpler problem is that you can do sampling. So once you know that what you're looking for is just 50% of the data being available, you're actually able to just maybe try downloading like a few pieces and get like some higher confidence or like high confidence that the whole thing is actually available. Now there's some subtleties here. It's not so easy to individually get a really high confidence, because someone could always just give you exactly the data that you're asking for and not actually reveal the whole thing. But when you have a lot of nodes that are doing this, then kind of collectively you can get like really good guarantees. But yeah, then based on this idea, essentially the goal would be that full nodes should only download like a few chunks of the data, or like some smaller than whole portion of the data eventually. And how do we plan to do this in practice? Like that's that's just one blob. In practice, we have a bunch of blobs. The first step would be to basically just create this kind of matrix from blobs, just stacking them on top of each other. Each one would be like horizontally extended with this erasure coding that I mentioned. And then sampling would be essentially columns. So, kind of the same as this, but extended vertically to the whole matrix. And so one way to think about this is that it's the same as if you were to individually sample each blob. So you kind of take each blob and you do some sampling, you randomly choose some indices to get. But in this case, you use the same choice of indices. So you just choose the randomness once. You say, okay, I want like, 2, 6, and whatever this is. And then you use the same choice for all of the rows. And so ultimately what it means is that you want to get a column as a sample. And yeah, basically, if 50%, we have the same thing that we had for individual blobs. If 50% of the columns are available, then the whole matrix is available. This is just because if 50% of the columns are available, then for each blob, 50% of the cells are available. Yeah, and these we'll call cells, the individual kind of pieces of a blob. And so yeah, this is kind of very high level, like what's one way that one might go about doing sampling for the whole set of blobs that we have. Then the question is, how do we actually incorporate this in the protocol? Like, where does this actually fit? Before we had this like more detailed picture with all the networking things and so on. And so one way to think about it is that there's more or less 3 kind of phases that we need to worry about, and then we'll like actually make these more specific and like put them in the right places in the protocol. The first phase is distribution. So at some point, there's going to be a builder or proposer that has all of these data and needs to send it out to the network. So this before in 4844 is just this like subnet system that we have. So yeah, that's one question. Like, how do you push out the data to the network actually? Then how do full nodes validators, like whoever is actually doing some sampling, how do they get the samples that they need? Like, okay, I want this column. Where do I get this column from? Like maybe the data exists somewhere, but then yeah, how do I actually get the piece that I want? And then the final piece is reconstruction. So, I mean, the whole point is that the data might actually be less than 100% available. It might be that not all of the columns are available. There's some they're missing. And in that case, the whole point is that we should be able to reconstruct, but not only we should be able to reconstruct, we actually need to do it and kind of heal the network. Like you can see, here, this red kind of sick network where some columns are missing. Eventually, we want to actually get to this healthy network where like everything is reconstructed. And then later we'll talk about more specifically about the kind of timelines of how fast this needs to happen. And yeah, that's kind of an introduction, but now let's more dig into details of what's happening specifically in Fusaka with GIS. So the first thing is the first phase that I talked about, distribution, and the second phase, sampling. They're essentially one and the same. They're merged. And actually, it looks very much like in 4844. So we have still this like kind of subnet structure with these gossip topics that are kind of, again, in parallel, more or less. But in this case, so there's 2 big differences. One is that before we were sending blobs. So we were sending these like basically blue rows, like the blue part of the rows is what we were sending in these subnets. Now things are basically, instead of being horizontal, they're vertical. So we're sending columns. So we kind of stack these blobs on top of each other. We do this erasure coding, and then we send out the vertical pieces. So that's one difference. And then the other difference is that we're actually doing sampling in the sense that you only participate in a few of these subnets. And so, for example, in this case, there's a bunch of these, but I'm only getting this piece and this piece, which is what I would have kind of wanted to sample. And then the other piece is reconstruction. And so the way that it's meant to work in Fusaka is with this one-of-n honesty assumption. And specifically, the set of people that we're making, or actors that we're making this assumption about, is nodes that are willing to participate in all of the subnets, not just sample, but like really participate in all of the subnets, download all of the data, reconstruct it, and reseed it if needed. So if the data is missing, basically there has to be this node that actually is in all of the subnets, so gets all of the columns that are actually there, does the reconstruction, and then reseeds and kind of helps heal the network. Now, of course, it doesn't have to be a single node that like carries this whole load, but and yeah, if there were multiple of them, this would be better. Some of them can send some columns, some that can send other columns. They can all help out with the reseeding. But then the point is that the assumption is just that there is a single node that does this. Yeah, so let's look at this in comparison to what we had before with 4844. As I already said, like, yeah, blobs are horizontally extended. So we have this like orange part and this kind of 2x like size increase that comes from this. We don't have this horizontal blob subnets. We have the vertical column subnets, and specifically we have actually 128 of them. Like this is how the blobs are chunked. So one other small difference that it's not just like it's not just this vertical horizontal thing. It's really this quantitative difference that we only have a few blob subnets. Like today we have 6 of them because there's at most 6 blobs, whereas here we start having like a much higher number of subnets. We have now 128. And yeah, and then the sampling, you only participate in a subset of them. And so specifically the number of subnets that you participate in, which is essentially your sampling count, is 8. So this is the minimum, like you at least sample 8 columns. And this is basically for security reasons. It's something where we can say, okay, if everyone is doing this, there's kind of high collective assurances about the data being available. Or rather, like another way to put it is that you can at most trick a small percentage of nodes into making a mistake about availability, basically. And yeah, basically, what does this mean? 8 out of 128. So this is 1/16 of all of the columns. But because of the 2x extension, this is 1/8 of the original data. So with the current parameters, basically what you get in terms of basically a factor of bandwidth improvement, like higher kind of bandwidth efficiency for sampling nodes, is 8x essentially. And I mean, same thing for storage, that you only need to store it like 1/8 of the original data essentially. But so that's for nodes that are sampling. Not all nodes are sampling. Specifically, I mean, full nodes are definitely sampling. Nodes with a few validators are also sampling, so they only do this minimum amount of work. There is this concept of validator custody where nodes can do more than the minimum, or like their basically default behavior through that the clients will actually have is that they will do more than the minimum proportional to their stake. So if you have a lot of stake, you'll basically download more columns. And specifically, if you have, I mean, this is the kind of current formula. You download. Oh, sorry, this should be max, but yeah, like max of 8 and validator count. So if you have more than 8 validators, you download like a bit more than a minimum, and once you have hundreds of validators, like for example 128, you actually download the whole data. So this also helps create this like default set of nodes that are actually fulfilling that 1/n reconstruction assumption that we talked about, because if you do participate in all the subnets, then by default, you're actually helping with reconstruction, and like not only. And yeah, so we mentioned this like 8x improvement factor for nodes that are sampling. For nodes that are not sampling, of course, you don't get this improvement factor, but these nodes are kind of meant, the idea is that they would be on the higher end of basically bandwidth requirements compared to like a random full node. And you still actually do get some benefits for even at this higher end of nodes that are not sampling. The reason is basically that when you think about it in terms of these nodes that download everything, you can think about it as there's this giant message that they're trying to, so they're really interested in the whole message in this case, because they're participating in all of the subnets. And you can think of it as like there's this giant message that they're trying to get essentially to like propagate around. And this message has been erasure coded and split into 128 pieces. And this is a much better way to do propagation than what 4844 does. I'm not going to go into detail of this, but like essentially from the perspective of these nodes, like we've kind of, you could think of it as like we implemented like a more efficient propagation system for them. Basically just generally like doing smaller pieces in erasure coding like just works better as a way to spread data around. And like from the perspective of the nodes that want all of the data, then this is what it looks like essentially. And then, yeah, let's finally get to a bit more the details of reconstruction. So let's think about a case where we have a proposer which maybe is malicious, or a builder which is malicious. It proposes some data that's not fully available. So these black columns again are not available, but it's more than 50% available. So this is a case where the data might actually be accepted by some nodes. So here there's some beacon nodes, and a bunch of them are actually thinking that the data is available. The reason is because they're doing sampling, but they might be, just avoiding these columns, or these columns might be like a small percentage of the total columns. So you might still end up with a lot of people thinking that it's available, but there's someone that doesn't think so. Still, this block is going to get a bunch of votes, again, because there's a lot of people that think that it's available. And so it's going to stick in the chain. Probably we want to kind of heal the network. And so the idea is that this kind of availability state is what exists at the attestation deadline. At this point, basically, once it is greater than 50% available, there's this node that actually gets all of the available columns, does the reconstructing and reseeding. And as all of this time, like between the basically attestation deadline and the next slot, like the next time that a proposer needs to come in and do their job to do reconstruction, to do the full reconstruction pipeline of like reconstruction and reseeding. And yeah, so we eventually get to this kind of healed network, and everyone actually passes the availability check. And importantly, the proposer also passes the availability check, because if there had been no reconstruction, and let's imagine that this guy was the proposer here, then this guy would have actually made a mistake in their fourth choice, because it would have thought that the data is not available, though most other people think that it's available. So here basically you can see why it's important to have reconstruction, because you cannot have people disagreeing on what the correct view of the world is, specifically with respect to availability. So if most people accept that something is available, you want everyone to accept that something is available. And the first instance where this is actually important is the next proposer. Like it's kind of the first case where someone might make a decision that's based on their local view of availability, which really should be correct and agreeing with everyone else's. So this is why this is the reconstruction time essentially. So in practice, this is 8 seconds, and I think we think that it's plenty of time for this to happen. And one reason to think this is the data in the first place is only supposed to take 4 seconds to propagate, at most, ideally less. And reconstruction itself does not take that long. So yeah, that's why 8 seconds in principle should be plenty for this to happen. Yeah, again, let's look at our high level picture. So we've kind of dug into this consensus layer side. Now maybe let's look at what's happening on the execution layer side. And so in particular, the mempool, like what essentially is for the the purpose of DAS or PeerDAS, the only part of the execution layer that's actually relevant, that changes, is possibly something in the mempool. So one thing that you might have noticed is that, well, we actually only change what's happening in the consensus layer side once with this column kind of structure and sampling. There is no sampling in the picture in the YEL. And so yeah, in the YEL mempool, blobs are still being fully downloaded, which is kind of the thing that originally we didn't want in the consensus layer. One question is does that not nullify the point of doing sampling? Are we just doing sampling on the CL while the bottleneck is actually on the EL at this point? And so there's a few reasons why this is actually not as straightforward as this. It really sounds that straightforward. Here you're downloading all of the things, and here you're not. What's the point of the latter? But it's not quite as simple. And so the reason is because on the YEL mempool, first of all, there's no strict deadline for things to propagate. So you eventually do want the transaction to propagate, but it doesn't have this kind of deadline given by the attestation deadline. So you don't have this a strict kind of 4 seconds that things need to happen in the critical path for the CL. You can already see it from the critical path wording. There's no such thing as critical path in the mempool. Things just eventually need to get around. Yeah, because of the fact that there's no strict deadline, We also can kind of be more lax, relaxed about propagation in the mempool. So you don't you basically announce that you have a blob transaction and then let the receiver say if they want it or not. Like you send them the transaction and then they say, do I actually want the blob that's associated with it? Yeah, you don't, people don't just like send you immediately everything that they have. And so this means that there's no duplication essentially. So you only, if you request a transaction from someone, you get it, that they're the only person that actually sends it to you. On the CL instead, because things are much more compressed in terms of timelines, so this issue of being in the critical path, we have this push kind of model propagation where once you get something, you immediately forward it to all of your mesh peers, like these kind of peers that you have in your topic, this like 8 nodes that I mentioned before. And so this leads to a lot of duplicate messages, in principle up to 8 essentially. And yeah, this kind of means that a lot of bandwidth can be wasted because a lot of you might be downloading 8 copies of the same thing. People might be sending out 8 copies of the same thing, even when actually a lot of their peers don't need them, and so on. And so there's like these things compound together, these two effects, to mean that the YEL mempool can actually in principle tolerate like a much higher number of blobs. So thinking about the YEL mempool, there is this number that's, I mean, or generally for DAS, there's this number that's gone around of 48 blobs. I probably won't explain. I mean, yeah, I can actually explain where it comes from. It comes from the spectra target being 6, and then this 8x factor that I mentioned before that comes from sampling. And so 6 times 8, 48. It doesn't actually mean that 48 is the right number. It's just from that narrow perspective, this would be like the number that gives you the same bandwidth for sampling nodes. But yeah, this is a number that's gone around, so let's just use this number. Even if you add 48 blobs, which I think would be like a pretty ambitious target for Fusaka, maybe we'll get there at some point. I don't think immediately on release, but even then, like in the mempool, this would only corresponds to 4 megabits per second. It's not nothing, but it's clearly also not like something that like blows up the whole system. And this just because we have like 12 seconds to kind of spread out this load over, and there's no duplication. On the CL, the same thing would mean, first of all, it has to propagate in 4 seconds. So now we're already talking about 12 megabits. And you also have the duplication factor. So duplication factors might be something between like 3 to 8, something along these lines. So you might get like 10 to 20 or even more kind of less efficiency on the CL than in the mempool. And so yeah, where I mean, still, if we did want to kind of try to limit as much as possible any problem coming from the mempool, one thing that we could do that's could be quite simple is to basically allow some rate limit, like local rate limiting, where you just set that you only want to give this much bandwidth to your blob mempool, and you basically don't pull blobs at a higher rate than that. So maybe you only want to use 2 megabits per second for the mempool, then you will only pull at most 48 blobs per slot. Or you can set the kind of per time rate of how many blobs you actually try to pull. And in the medium term, there's kind of other ideas. I mean, one thing is that it's unclear exactly what roles will the mempool play in the future. I think it will always play at least a role of censorship resistance fallback, but it's not clear if it's going to have a bigger role beyond that. I think likely it will because of what I mentioned, that actually sending things in a mempool can be very efficient as kind of a pre-propagation step. And so yeah, I think in principle it would be nice if we could make use of this. And so there's some ideas around what might be called mempool sampling. So yeah, basically introducing sampling concepts also to the mempool, matching kind of what's happening on the CL, but out of the critical path. So basically get the benefits of sampling, also get the benefits of doing things out of the critical path, essentially. So basically allow blob propagation, broadly speaking, to happen kind of in this more relaxed way in advance of the critical path. Yeah, so now we've kind of covered the consensus layer. at broad strokes, the execution layer, at least as you know, as to what's happening with respect to the mempool, and which is most of what's relevant to PeerDAS. And kind of we have now this green box of basically building. Yeah, let's kind of dig into that. So there is a few things that you need to do to build a block. One, we've already talked about, so we'll skip it. You need to run a mempool. So as long as that's a feasible thing to do, that's not something that you have to worry about too much. In fact, we also maybe need to worry about it even less in some sense, in the sense that you don't actually even need to run a mempool all the time in order to build blocks at high blob counts. You could even, for example, just say, okay, most of the time I actually am implementing these rate limits, if you have reasons to do so. But when it's my turn to build, then I'm going to like fully try to get as many blobs as I can. And again, as I said, this doesn't require like a crazy amount of peak bandwidth. For example, it could be something that makes sense if you're concerned about kind of sustained bandwidth consumption, like you really have, you have like data limits or something like that, like monthly limits. Then yeah, you could say, okay, I can actually only when I'm proposing like fully just try to participate in the mempool, like pull anything that I see, get as many blocks as I can, and then try to build kind of the best block that I can, if that's your limitation. Then there's this other part that it's basically that we haven't talked about at all, and so this now maybe doesn't make sense. What even it's saying, KZG proofs for cells and like needing to compute them, and we'll get into this. And yeah, the last part is that you have to be able to push out the data fast enough. So this kind of what we talked about on the CL in the critical path, you have to quickly send out data so that it propagates in the network by the attestation deadline. So these are kind of the key components of block building, at least the DAS part of block building. And yeah, for let's get into the cell proof stuff. So this is something that so far we've just omitted when talking about sampling. So okay, you were on the CL, you're subscribed to these subnets, you want to get these columns, you get them. Now, how do you actually verify that these columns are really the right data that actually matches the KZG commitments in the block? And yeah, basically, I mean, I guess a brief word about KZG commitments. These are basically just the little pieces of data that we have in blocks that basically that commit to which blobs the block has. Like the block doesn't contain the blobs, it contains only the commitments. You can think of this as like Merkle roots or hashes, but like with deeper cryptographic powers. Essentially, yeah, it basically just lets the block contain only like tiny amounts of data, but still commit to a certain set of blobs. And so given a certain KZG commitment so here we would have a KZG commitment for this blob, a KZG commitment for this blob, and for all of them, for the whole list. And this is already the case in the current system in 4844. You would want to be able to get this column and know that it actually corresponds to the right commitments, even without having the whole blob. Like, of course, if you had the whole blob, you could check that a blob corresponds to the commitment. But yeah, now you have only like a piece, and kind of have this issue of how do you do this. And so in practice, how you do this is with proofs. The cryptographic box that I'm not going to like fully or almost at all open around KZG, but what this looks like on the network level and like what a node is doing is that when you're subscribed to one of these subnets and you get something like this column, you actually don't just get the column, you get the column, but in this bundle with commitments. So this is like this little thing that commits to the whole row, so not or to the whole blob, not just to this part, but to the whole thing, and then a proof. And this proof is basically what we were calling cell KZG proof. So it's a KZG proof for specifically this cell. And so what this does essentially, it lets you prove in opening of a commitment at a certain specific index. So it lets you say, okay, there's this blob, extended blob, it corresponds to this commitment. I supposedly I have a cell for index, in this case 3 or well, 2. So yeah, supposedly someone's giving me this cell. They're claiming that it is the actual value of this blob at this index. So blob of I equals cell essentially, and it gives me this extra piece of information, this proof that I can use it to verify that. So given the commitment, the proof, the blob, and the index, I can check that actually without needing all of these other pieces of data, like the rest of the blob. I can check that yes, that claim is true. This thing is really the value that this blob has at this index, and then you can apply this to the whole column. So you have one proof per column as here, and you check that the whole column is what it says that it is essentially. And yeah, one thing to know about Salk-Kaziji proofs is that, I mean, they're proofs. The whole point is there's an asymmetry to some extent between computation and verification. And so proof verification is quite fast, like even an individual one. I think it's like 1 to 3 milliseconds, depending on which hardware. And also, importantly, because there's a lot of these, like each cell has one proof. So yeah, you have like for each blob, you have 128 and then many blobs. So batching is very effective. So if you have 64 blobs, it takes about this much, let's say half a second, to verify all of the cells, and this is without even parallelizing the computation. So in principle, verification it's not so bad. And I mean, even you don't actually need to verify all of the cells. You only need to verify a certain set of columns that you're sampling if you're a sampling node. But yeah, proof computation on the other hand, it's quite slow. It is perfectly parallelizable because you have a bunch of blobs and each blob is completely independent. So you can do the proof computation for each blob completely in parallel, but still it's quite slow. Like on a single blob, it's about this much, like 150 to 200 milliseconds to compute this like 128 proofs. So this, you can see that, if you add 20 blobs, this is 4 seconds. If you have 100 blobs, this 20 seconds, like it adds up, even with parallelization. And so this is a bit of an issue because by default, where this would happen is here in the critical path. So we've left everything here kind of basically unchanged on the mempool. So you get these blobs like as normally as it happens today. They end up in the proposer and get sent to the engine API and so on. At some point, you have to take these blobs and convert them into this matrix with proofs. So doing the extension, this turning the blue thing into also the orange thing, like having the redundancy, it's quite fast. But then computing the proofs, as I said, it's quite slow. So the issue is, yeah, that this is really happening, or I mean, by default, it would be happening in part of these like critical 4 seconds where things are really supposed to be like fast and kind of making sure that you meet the deadline. And so that's the worst place to put like a very computationally expensive operation. And then, yeah, I mean, just as a note, like, here, this is meant to be 1 proof per cell. So this would be like, 1 here, and so on. And same here, this would be 1 proof per cell for the whole column. And yeah, you then send out the cells, as I said, in kind of as a bundle with the column. And once you get to the attester is going to use this to verify that they actually got the right piece of information. But yeah, so as I said, it's not ideal that this is in the critical path. In fact, it doesn't need to be in the critical path, and part of the design, and this is really like a part that's been actively worked on in the sense of basically the spec is being finalized around this. There's kind of active discussions around more like details of this, but it's now really part of the PeerDAS design for Fusaka to actually take this out of the critical path. And the way this is done is basically that you push proof computation to the senders. So there's someone that's submitting this transaction in the mempool. They can actually just do the computation for their blob. Like they can extend the blob, compute all the proofs, submit all of the proofs to the mempool. Because we have this asymmetry, like computation is slow, verification is fast. So if someone does the job kind of at the edge when sending the transaction, then the proofs going around the network isn't so bad. Like verification is fast. They're also very small. One very good thing about KZG is that basically, yeah, the proof size is really tiny. It's like 48 bytes. So yeah, it adds like very little overhead. And yeah, it's 48 bytes for a cell, which currently is 2 kilobytes. So it's really small kind of overhead. Yeah, so with this kind of architecture, the cell proof computation would be both out of the critical path and distributed. Like now there's no single actor which actually needs to, it's not the builder anymore, it's not the proposer, it's not even like specific nodes in the mempool, it's whoever is actually originating the transactions, and these are different actors and also like generally well-resourced, but even without thinking about that, it's just something that can be done by a lot of actors, and it's not time critical even, because when you send a transaction, well, if you need to do the proof computation, it's just going to take a bit longer to send the transaction. And so, yeah, this basically is what the current design looks like, which is you still have these proofs, like on the CL, everything is the same. You eventually do want, everything to go with the proofs and so on, but the proofs are coming in from here. They're not computed in this part of the design. So yeah, basically, maybe this is like the StarkNet sequencer or something. It's generating a transaction, it's computing the proof, and it's submitting it to the mempool. And this is another rollup or whoever, and they're doing the proof themselves. And then here, there's only verification happening, and everything is passed to the proposer, which again only needs to do verification. And yeah, so now we've kind of gone through the mempool part of things, gone through this proof computation kind of sidetrack. And we're back to the problem of, on the CL side, of being able to actually push out the data fast enough. And so this is a bit challenging because now, well, there's kind of two reasons. One is we're adding a 2x factor. So there is this, orange thing that you also need to send out. And so, yeah, we've already coded the data. This is great for sampling, reconstruction, and so on. But when you need to send it, it's now 2x the original amount. And also because, yeah, you need to send it to 8 peers. Like, as I said before, in each of these subnets, you kind of, when you propagate, you send out to 8 peers. And so you have this like big factor of kind of overhead from that. So at the end of the day, you essentially need to send out 16 times more than the original size. So actually, even 50 blobs, it's not that much data. It's 50 megabits. So, not even like, yeah, whatever that is, 6 megabytes. But once you add the 16x factor, that actually becomes quite a lot. Like if you need to send out all of the data in 1 second to all of of these 8 peers and so on, now it would require the 800 megabits upload, which starts to be pretty significant. For local block builders is, for the most part, pretty much, not unattainable. There's people that have gigabit, but like, of course, this is not something that that's within like reasonable requirements, essentially, at least again for local block builders. And so, yeah, the question is that the bottleneck? Can kind of jump ahead a little bit. Yeah, one important thing to keep in mind is whether we're worried about local block building versus building in general. I would say let's just worry about local block building specifically. When it comes to like a MEV boost builder, they can kind of figure it out. It's, yeah, even that amount of even that bandwidth is really not something like too prohibitive for them. And there's other things that you can do to, like, it can be pushed out from different nodes, but yeah, like there's also, there's even other kind of techniques that make things better. You don't actually need to send the data to 8 peers, strictly speaking, but kind of beyond the scope of this. But yeah, the main worry is really local block building. Like, to some extent, whatever you think about local block building, we at least want to enable building to be possible, not in a data center. It doesn't mean that everyone should be able to do it, like no matter what kind of bandwidth they have. But yeah, certainly not that kind of the requirements cannot be as high as that, or like nowhere near as high as that. If we want to ensure that no matter what, someone will be doing the job, essentially. And so one thing that's kind of critical here is that when you build locally, all of the blobs are coming from the mempool. Like, you don't have access to kind of private mempools. If you imagine like an entity, like a just Sol Staker or something like that, they just get blobs from the mempool. That's the only source of blobs that they actually have. And so one thing that we can do with that is, well, the blobs do already exist in the mempool, essentially. So, the whole problem here is the proposer needing to push out the blobs to other people. but actually the proposer is getting the blobs from a network, this separate like YEL network where they already exist. So they in some sense, there's maybe no need to actually repropagate them. And so one thing we can do, which I mean, actually this already happens in 4844, but it's like not as critical, let's say, is that, yeah, you could just send out the block. Then anyone that gets the block now knows which blobs they're supposed to get because the block has these commitments, and you can basically request it from your YEL node. So your YEL node is running a mempool, hopefully already has all of the blobs, and can just basically send them to you, and you kind of get all whatever columns you might need. Now this is a bit of a naive version of this. There's a big limitation, which is that if you miss even a single blob, then you're unable to reconstruct the columns. Like, let's say you miss this one, now you would miss this whole kind of row. It's not useful to have only like a partial set of blobs. Like all of your sampling would fail. Like you would not even be able to get a single column because you're missing some pieces for all of them. And so, yeah, we can actually do better than this. Yeah, this is what's called distributed blob publishing. Basically, it's the same idea, but with the twist that you don't rely on everyone just being able to do this polling successfully and get everything that they need. You rely that on someone being able to do this, like someone having all of the blobs or like a few nodes and so on, and then helping to propagate the columns. So someone should successfully be able to do this and then kind of repropagate the data on the CL. So one way to think about it is basically the proposer sends out the block, and it's almost like a request to help him with the propagation. So it's you kind of outsourcing the task of propagating columns to anyone that actually is able to get all of the blobs from the mempool. So yeah, basically in this case, okay, you get the blobs from the mempool. Maybe you only use blobs that have been there for like a little bit of time, so that you're more sure that someone should have all of them. Then there is at least this one node that is actually successfully able to go through this process, request the blobs from its YEL node, get the whole matrix. And then this one person now kind of acts as the proposer was supposed to be. So it actually does this step of like propagating everything. So there's kind of this like, extra step before getting to this actual propagation on the CL. And eventually, yeah, things still get to the attester and they attest. And it can actually look better than this even because it doesn't have to be a single node that does this. There could be a bunch of nodes. They're all kind of successfully able to do this. And then these nodes don't even need to be subscribed to all of the subnets. For example, this node, even though it does get all of the data from the YEL, again, there's a bit of symmetry between the YEL and the CL, where on the CL, you might care about only a subset of the data. On the YEL, you always have all of the data at this point. So you get all of the data, but then you maybe only propagate this one column. And then this other node propagates this column, this other node propagates this column. So different parts of the network can kind of act as repropagation points for specific portions of the data that they care about. And then maybe there's some nodes that just care about all of the data and they kind of push it all out. So there can be a bit of like essentially a bunch of repropagation points throughout the network that actually make this whole essentially much more efficient. So as long as there's like enough people that have all of these blobs, so as long as these blobs are well distributed in the mempool, then on the CL, things should basically take care of themselves. Like people will kind of boost propagation to the nodes that maybe are missing some of them. And yeah, I mean, with this, I think, and I mean, this very much, again, part of the active, things that are being worked on actively and where there's a lot of interest in doing testing. I mean, really, like it's something that's being worked on right now, being tested right now. But yeah, the idea would be that through this kind of mechanism, it should still be possible to do local block building even at relatively high blob counts without actually needing a lot, like a big upload connection. And yeah, with that, I think we've gone through a lot of the bottlenecks, a lot of the kind of interesting parts of the design and motivated why they're there, what's left. But basically just a bit of implementation. As I said, this get blobs part that I just mentioned is actively being worked on. There's a little bit of work on this transaction proof computation and like pushing it to the edges. But really, like I would say most of it is just a lot of testing, a lot of stress testing, a lot of figuring out what actually is the real behavior of some of these things in a network and in a real network at scale. And then figuring out from there what things need to be kind of tweaked and how far even we can push things, like how many blobs can we actually support safely. And so there's definitely a lot of work, but I think the design is essentially done at this point for Fusaka. And there's just a lot of work left in actually basically figuring out what's the best shape that this can be shipped in. And then I mean there's a lot of still research work and so on, or R&D work in figuring out then what's next. There's a lot of ideas which unfortunately I didn't have time to cover. I decided that it would be interesting, given where we're at in the cycle, to more focus on the details of the current design. But for another time, I think there's a lot to say about the next steps essentially. And I think maybe in a few months we might have even a clearer idea of what's the right thing to kind of do next. And thanks everyone. Again, thanks for inviting me. You can find here at das.wtf a lot of resources that people have helpfully compiled, other talks and other kind of, there's also a link to another website that's called das.atm, where it's much more like in the process, like it's almost like a PM kind of website with like what's going on with PeerDust right now, like really current issues, breakout calls, like all these things. I don't know exactly what the audience looks like, but maybe there's someone, some of you out there that really are kind of taking interest in seeing like what's going on. Even maybe some of you can help, and you're welcome to. So lots of resources here. If you and I mean, of course, if you have any questions about anything, you can reach me on Twitter, possibly. That's at FRADAMT. Sorry, didn't think to write it on the slides, but somehow hopefully you can find a way to reach me, and feel free to ask questions. Again, thank you. And should I show the slides you?
Let's do questions first, and then
Oh
we
yeah.
can show
Yeah.
the end slides.
Okay.
So I know I've got some questions. So first of all, thank you for a great talk. I know I learned heaps, and it's really good to see where things are headed. And the design makes a lot of sense to me. So that's really good. Chris, Paul, Joanne, do you have any questions? Okay, let's say we've got no questions from them, I think. So one thing that you didn't talk to is, so I know that some of the blobs end up being only partially full, because essentially say a roll up, they sign up to a particular blob, and then so they might only half fill a blob. So is there some sort of compression technique to handle the fact that the blob might only be half full? Thus reducing the amount of data that needs to be pushed around.
Interesting. It's a good question. I mean, I definitely don't think we have something along these lines. I mean, there is snappy compression, I think pretty much used by all clients for sending things around in the network. But I'm not sure if it would actually help in the case of blob specifically. Because
Because I mean, normally the transactions are compressed, and if it was base rolling up, chances are they're going to have full blobs. But then some of the other roll-up systems, they might post a blob, but it might not be full. So there might be a whole heap of zeros, in it, which, you could just run length code or something really simple. But
I'm not sure. It's a
yeah,
good question. I don't think there is something like that right now. I mean, there is this like compression by kind of
yeah.
default that's used on all networking, but I don't think there's something like specific for blobs.
Yeah, because I mean, I guess you're going to do the Reed-Solomon coding to expand up the data, and when you do that, then it's, it's like it's gone through a hash function or something. So it'll
Yeah, I
be,
mean, yeah,
you
on
know,
the
but-
expansion side, yeah, I think there's
yeah.
probably nothing
So
that you
so
can
you'd
do
have to
about
do it
it.
before the expansion, but
Yeah.
then I guess if the whole system assumes full blobs, then maybe it just makes things more complicated. Yeah. Um, so another thing I wrote earlier in the talk, which I think I've answered my own question, but so if the blobs were split up, rather than 128 pieces, it was 256 pieces, would that be better, or is there some trade-off about the number of splits?
Yeah, so there is a trade-off. I think it's likely that at least for 256, it would be better. I think the idea partially with 128 is to start with something a bit closer to what we're already kind of used to. Like we have 64 subnets when it comes to attestations. I mean that's one thing, but also just to yeah, like not kind of immediately try to push things too much. But yeah, part of the trade-off is proof computation. So the more you split, the more proofs you have, because you have a proof for each cell,
Yeah.
like for each like minimal thing that can be kind of go by itself essentially. And so yeah, proof computation just would take quite a bit longer the more you split. I think we consider it up to 512, and yeah, it's much worse. And I don't remember the exact factor, but yeah, I think it might
Yeah.
even be like about linearly worse. Yeah, which would make sense. And so that's one thing. The other thing is you get a bit more overhead on the networking side, because now you have a proof per smaller unit. So before it was 48 bytes proof, plus also 48 byte commitment per 2 kilobytes cell, and now it's 1 kilobyte, and with 512 it becomes like 500 bytes, so it becomes even like actually pretty real overhead. Like between the proof and the commitment, it becomes like 20% overhead. So that's another thing. And then, I mean, one other point is it only helps the samplers um, to 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 make the columns thinner, not the nodes that are kind of participating in all subnets. For them, it's actually just worse, because now you have more overhead, but still the same amount of data. But still, I think it's quite possible that we might in a later iteration like change this parameter to something bigger, precisely
Yeah.
to help the samplers.
Yeah, and you could imagine, I guess, if you had, say, so there are bases, obviously, like a huge roll up, but there are others, and so maybe if there were multiple sized blobs, like so there were large blobs and normal blobs, and because at the moment I think base uses something like 2 or 3 blobs per block every block as in its roll up, and I think um Arbitrum 1 uses a whole heap as well, like 1 or 2 per block every block. So you could imagine for those roll-ups with lots and lots of transactions, if there was a big blob. So I know it again complicates the design if you had two sizes of blobs, but I wonder if that would then mean if you had 256 splits, the actual data size would still be 2K, say, for instance. But yeah, anyway, the thoughts for the future, though, I guess. Um, yeah, it's good to see that
Yeah.
it's. Anyway, sorry.
Mm. No, no, yeah, sorry, go ahead.
Yeah, it's good to see how close it is, and how a lot of the thought things have been really. Yeah. Well, anyway, one other question that I had was around block times. So I know in the roadmap, the longer term roadmap for Ethereum, um, we've got 3 slot finality, but another part of it was trying to reduce the actual like slot time down. And I guess if as that slot time goes down, that 4 second propagation time for blobs would start to become like problematic, even if you were trying to get your slot time down to 1 second or 2 seconds. So yeah, so your thoughts on that?
Yeah, so I mean, one thing is that if we did decrease the slot time, it would also come with a proportional decrease in the total amount of data. So like, let's say the number of blobs that is pushed. So from like the bandwidth perspective, things should be more essentially stay the same. There is the latency part of it, which is still like, there's a few hops that things need to go through the network, and like part of the cost is just the bandwidth, but part of the cost is just the latency, and the latency part, it doesn't matter how big the data is, it still exists. So you kind of have this fixed cost of latency that becomes bigger. So it definitely would impact things if you shrunk the time a lot. But yeah, I mean, I think it's still quite, like, I think there's a lot of work to do to really figure out, like, concretely, realistically, like what is a good way to reduce the slot times that much in a system like Ethereum. Like, of course, there's other blockchains that have much shorter slot times, but they also have like very different assumptions and so on. So I would say there's definitely a lot of work to do there.
Yeah, for sure, for sure. And I think, yeah, this is the thing. I think everyone needs to remember Ethereum is not Solana. Solana has different trade-offs to Ethereum. And yeah, I think that's where it is. Are there any other questions? Okay, let's flick to the next slides then, please.
Yeah, sorry, just give me 1 second. I'm gonna plug in my laptop because I think it might die before we get to the end.
Okay, all right. Not a problem at all. Yeah, so whilst Francesco is busily plugging in his laptop, I think everyone will agree that was a fantastic talk and that we know a lot more about peer DAS than we did before. Yes, some claps all around. Yeah.
Okay. Yeah.
Right, back in
Sorry, I
business.
should have just gone to the slide before before
No,
leaving,
no,
but yeah,
that's okay.
here it
That's
is.
okay. All right, there is a merch store. There isn't a Peer Daz shirt though. Maybe once the tech goes live in Fusaka, I'll come up with a new T-shirt. I'll think of an
Just
interesting design.
wait for the spec to be frozen.
Yeah, wait, yes. Otherwise, if I have the block diagram, it will all be wrong. Yeah. All right, next slide, please. All right. So in 2 weeks' time, we've got a talk on the 3-slot finality. Then 2 weeks more after that, we've got a deep dive analysis by our pseudo-anonymous auditor who has given us some great detail in a previous talk on hack, and is going to again do a really deep dive on how Bybit worked and try and talk to the strategies being used and, like look for patterns there. After that, we've got a talk which is about the intersection of AI and blockchain. After that, there's a talk by a ZK rollup infrastructure company. But anyway, we're just finalizing that. And then finally in June, I'm going to talk about the other part of Fusaka that is huge, that will change things dramatically, which is EOF, and give a deep dive on EOF and looking at exactly how that works. Next slide, please. And so if you're watching this live, it's available on YouTube. If you're watching this on YouTube and you want to ask the speakers tricky questions, join the meetup. There is a Slack workspace. And finally, for some things, there is example code, which will be in that repo. And that is all. So Francesco, thank you again. That was an excellent talk. I think we've all learnt a lot. So yeah, thank you.
Thanks again for inviting me. It was a pleasure.
Yeah. All right. Well, have a great day. And I'll send you the
You
link
too.
to the video on YouTube when it's available, which should be in about 24 hours.
All right, great.
All right.
Thank
Thank
you.
you. Bye-bye.